So today I'm going to tell you about a bit of work that I've done in my PhD with David Sabak, looking at minimum work control protocols, and we're going to be looking at this particular Ising model system. But before we get started, I just want to say that in general, what I'm interested in is how does a system get over some energy barrier that separates two metastable conformations. So when we're thinking about a control protocol, one way that we can get the system over this energy barrier is by driving it. So we could have some sort of time-dependent external potential that by varying some parameter of the system, so in this case we're looking at a harmonic trap, and you can move the center of the trap from one end to the other in order to drive the system between the metastable states. Now control protocols can be implemented in experiment or simulation, which makes them very broadly applicable. You can also imagine pushing on all sorts of different systems. So we've heard a couple things about pulling proteins or different biomolecules apart. These are examples of control protocols where you're putting work into the system to induce some sort of conformational change. Now, when you do these driving protocols in finite time, the second law of thermodynamics dictates that you have to do excess work on the system above the equilibrium free energy change between the two endpoints of your control protocol. However, despite the fact that these control protocols are driving the system out of equilibrium, we can still extract useful equilibrium information about the system of interest. So using things like Jarzynski's equality, we can learn about equilibrium for energy differences between the different conformations of your molecules. So this makes it a useful quantitative tool as well for learning about underlying system energetics. And what we're interested in a lot in our group is really understanding the energetic costs of control. So how does the way that you do the driving affect how dissipative the process is? So what I'm going to focus on today is looking at driving protocols where you have multiple knobs with which to perturb your system, so multiple control parameters to change its conformational state. And part of the motivation for that is because a lot of the systems that we're interested in are high dimensional, and there's multiple coordinates, multiple degrees of freedom that are moving collectively as the system is going over the energy barrier. So if we can have multiple control parameters that are connecting to these different degrees of freedom, how does that affect the energetic cost of the driving? And in particular, we're going to be looking at protocols that minimize the work that you do on the system. So this is the particular model system that I'll be talking about today. So it's a 3x3 Ising model. Basically, these 9 colored spins on the inside are the ones that are fluctuating, and the gray spins on the outside are fixed boundary conditions. So you can see that the vertical edges have spin up boundary conditions, and the horizontal edges have spin down boundary conditions. So this is a ferromagnetic Ising model, which means that there are 2 stable states, one where all of the spins are in the spin down configuration and one where they're all up. We're going to be looking at driving the system between these 2 conformations. So to do this, we can just apply some magnetic fields to the system, and we're going to be contrasting a one-dimensional control with multi-dimensional control. So one-dimensional control, we just have one magnetic field applied to all of the individual spins, and the magnetic fields on all these spins are going to be changing at the same rate. And this is kind of a naive one-dimensional picture, but if we kind of look at the geometry of the system, in particular looking at the boundary conditions, these spins are all kind of different, and you might expect them to have different roles in when the system is overcoming the energy barrier. So in addition to contrast this one-dimensional picture, we're going to be looking at a 4-dimensional control protocol where we have 4 different magnetic fields that are being applied to the spins of the same symmetry type. So those are indicated by the colors on this diagram. And there's going to be freedom to drive these different colored spins in different ways. So what we're going to be looking at basically optimizing the work that we do on the system during these protocols and minimizing it as much as possible. And the main question that we're going to be kind of looking at today in this kind of brief talk is just what's the difference between how the multidimensional controller is driving the system as opposed to a one-dimensional controller. So how do we talk about minimum work control protocols in this sort of context? So when the protocol duration is long enough that your system is close to equilibrium, not quite in equilibrium, but close to equilibrium, the excess work during the control protocol can be approximated with linear response theory to have this particular form. So for the excess work depends on the protocol duration. So delta T is protocol duration, and you basically integrate for every point in time, what is the change in each of the control parameters? So HI is indexing each of the control parameters that you're individually changing during the protocol. And then the other term here in the middle is this generalized friction. And this is basically an integrated time correlation function of fluctuations in your system. In this case, the conjugate forces to the control parameters, which are the magnetic fields, is just the magnetization of each of the spins that we're driving. So basically, the fluctuations of the spins when they're flipping up and down throughout the control protocol is providing some resistance, which is what this friction tensor is quantifying. So to give a picture of what this friction kind of looks like for this system, we can't really look at a four-dimensional space very easily, so I'm just going to show you what this looks like for a two-dimensional space. So just where I have magnetic fields on the green spins and on the blue spins, so just a two-dimensional control parameter here. So we can look at our control parameter space, which is defined by the axes of what's the field on the blue spins, what's the field on the green spins. And then we can look at two protocols that go between two endpoints. So these are the endpoints that we chose for our control protocol. Here, the system is forced into the spin down configuration, and then at the other end of the control protocol, the system will be forced into the spin up configuration. So this is the control parameter space. We basically want to design protocols that minimize work in this space. So this generalized friction we just talked about is kind of the relevant quantity that needs to be optimized. So we can calculate this throughout this two-dimensional space. And we see that there's a peak in the friction over in this quadrant, and this is where the field on the blue spins is positive, so essentially counteracting that boundary condition that comes from that spin down, the adjacent down spin. And the green field likewise is negative and counteracts that boundary condition. So the friction is peaked basically where the system is most bistable and doesn't feel the effects of the boundary conditions as much. And then throughout the rest of the control parameter space, we see that the friction is lower, which is going to help us to figure out how to minimize work. So we are talking about a one-dimensional controller in this space. It's just a straight line between the two endpoints. So this is kind of just a naive protocol. You're just going to change all of the fields at the same velocity between the two endpoints. We can do a one-dimensional optimization of this path to minimize the work. So from this linear response approximation, basically the optimal control protocol velocity, so the optimal speed at which you change these fields, is inversely proportional to the friction. So you can see in the middle of this line where the friction is larger, these dots, which indicate points that are equally spaced in time, are closer together, meaning that the protocol is slowing down in that region. Now for the multidimensional optimization, we have to numerically solve the Euler-Lagrange equation, and basically this is the protocol that we get when we're just looking at the two-dimensional space here. So you can see that this multidimensional protocol is completely avoiding this peak in the friction and going through low friction regions of the control parameter space where the resistance to driving the system is lower. So this is the two-dimensional protocol. I'm going to talk more about results from the four-dimensional protocol. So just to show you what they look like, this is what's shown in the bottom right here. So we're looking at a time-optimized protocol where, again, you're looking at this straight line path between the endpoints, but you optimize the protocol speed to minimize the work. So here, again, we see that it slows down throughout the middle of the control protocol, again, to minimize the resistance where that friction is high. And then fully optimized four-dimensional protocol, we see that it looks very different. All the spins are being pushed on kind of independently and at separate times. And the general feature we see is that the green spins are being pushed on first and the blue spins are being pushed on later in the protocol. And this kind of makes sense because if we start with our system in this spin down configuration, these green spins are energetically, or the anti-alignment between the green spin and its boundary condition is energetically unfavorable. So it kind of makes sense that you'd want to start by pushing on those spins because they're easier to push on first. Okay, so what's the difference between how the system is actually driven in this one-dimensional case and the multi-dimensional case where there's many control parameters that you're using to drive the system? Sorry, one more thing first, just how well do these protocols do, the multi-dimensional control protocols do relative to the naive protocols where you're just changing all the fields at the same time? So that's what we're looking at here. We're comparing three protocols. One is just a naive protocol where all fields are changed at a constant velocity. The next one is the time optimization, where again all the fields are changed at the same time, but we have optimized the speed at which they are changing, and then this fully optimized four-dimensional control protocol. So to look at how well they do, we make a plot. This is a log-log plot of the excess work during the protocol, so the average excess work during the protocol, as a function of how long the protocol takes. So basically our protocols are optimized in this long duration limit, so where your driving is relatively slow. So looking at this top plot here, you can see that the naive protocols do the worst, obviously, because they are just naive. The time-optimized protocols, we can see they do a little bit better. They do a little bit less excess work than the naive protocols, but these fully optimized protocols do significantly better in terms of excess work. And they also relax to equilibrium a lot faster, to this linear response regime a lot faster. So to put actual numbers on how much better these protocols are than the naive protocol, we can look at the ratio of the excess work that's done during a naive protocol relative to one of these design protocols. And we see that when we do this time optimization without changing the spatial path of the system, the time optimized protocols basically do half the amount of work that's done in this naive protocol. But when you do this full optimization in multidimensional space, you get 26 times less work than the naive protocol. So it's a significant reduction in the amount of work that you're doing on the system. So now, how do these different protocols actually drive the system, and why are these multidimensional ones so much better? So one reason is they're just driving the system differently. So what we're looking at here is basically what's the mean state, the mean magnetization state of each of these spins, where -1 is a downspin and +1 is an upspin, as a function of the protocol duration. So there's more than two sets of curves, but the solid curves here are basically when we're looking in the quasi-static limit. So if we were to do this infinitely slowly and the system was in equilibrium the whole time, this would be the mean state of the system. And then each of the colored curves correspond to the color on the diagram in the top right. And then these dots are when we do some non-equilibrium simulations at a finite duration. So we see that in the naive and time-optimized protocols, more or less all of these spins are flipping at the same time throughout the control protocol. Whereas in this fully optimized protocol, we see very clearly that green spins flip first, red and black spins flip throughout the middle of the protocol, and the blue spins flip later. And that again makes sense when we consider the boundary conditions that are initially making these green spins energetically unstable. The second thing that we see from this is comparing the quasi-static limit of these protocols to their non-equilibrium simulations. These are all simulations that are done at the same protocol duration. We see that the fully optimized protocols are nearly at equilibrium, whereas the time-optimized and naive protocols are still significantly far from equilibrium. So that is one factor in why the excess work is reduced. We also see that these spins are driven differently. So one way to see this is by looking at the power that is input to each of these spins throughout the control protocols. So again, looking at the naive protocols, the simulations are the dotted lines, and the quasi-static limit are the solid lines here. And we see in the naive and time-optimized protocols, basically, the controller is dumping work in and then extracting it out. But it's doing the same thing to all of the different spins. Whereas in the fully optimized protocol, there's a much more elaborate schedule, and each spin is kind of being pushed on in accordance with its system relaxation. So just to conclude, when we're looking at multidimensional control parameter space, there's obviously a lot more flexibility in driving your system, but it also allows you to push on particular degrees of freedom that are perhaps have different roles in how the system is overcoming the energy barrier. So we found that these multidimensional control protocols significantly reduce the excess work. They also drive the system along a different pathway that is very fast relaxing, so the system stays close to equilibrium even for short protocol durations. And it pushes on these different spins differently depending on whether they need work to overcome some energy barriers. And all of this together just keeps the system close to equilibrium and reduces the excess work. So with that, I will thank my group members, the SFAC group, as well as funding sources, and especially the Digital Research Alliance of Canada, formerly Compute Canada, which did all the calculations for me, which took a while. So, thank you.